Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashley Martini. As always, the goal of this seminar series is to bring our community together. The seminars stream live on the third Thursday of every month at 11 a.m. Eastern Time. They're also available to watch anytime on the YouTube channel. We've had a great group of speakers over the past few years, and again, they're available for you to watch anytime on our YouTube channel. We also have some excellent speakers planned for the upcoming months, and then we hope that you will join us for all of them. Before we get started, a few acknowledgements. Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, Dr. Frankie Antolon, the Director of Education and Outreach, and two CMCC grad students without whom the seminar would not be possible, Ryan and Breyer. Thank you again for participating in this seminar series. Please do follow us along on the YouTube channel. Lastly, a few quick guidelines. Reminder that the webinar is being recorded. If you have any questions, you can either email them to us at cmccdiscussions@gmail.com or post them directly into the YouTube channel. Either way, they will be propagated to the speaker at the end of the seminar. And we hope that you will share your opinions about the seminar series with us for further improvement. Please feel free to use this QR code available here or also on the YouTube channel to provide feedback for continuous improvement. And last but not least, it's my great pleasure to welcome today's seminar speaker, a CMCC team member, Dr. James Rondinelli. Dr. Rondinelli is the Walter Dill Scott Professor and Associate Chair in the Department of Material Science and Engineering, where he also holds an appointment in the Applied Physics program. He leads the Materials Theory and Design Group and serves as Director of the Predictive Science and Engineering Design program. His research integrates electronic structure theory with materials design, focusing on transition metal compounds, alloys, and molecules. By uncovering picoscale structure property relationships, his work advances materials for structural, microelectronic, and quantum information systems technology. Rondinelli has received numerous awards, including the Presidential Early Career Award for Scientists and Engineers and the Materials Research Society Outstanding Young Investigator Award. He's a fellow of the American Physical Society, the Materials Research Society, and the American Association for Advancement of Science. He has authored over 330 peer-reviewed publications and holds 2 patents. Professor Rondinelli earned his bachelor's in material science and engineering from Northwestern University and his PhD in materials from the University of California, Santa Barbara. Prior to joining Northwestern, he was a Joseph Katz named fellow at Argonne National Laboratory and an assistant professor at Drexel University. Again, it is my great pleasure to welcome Dr. James Rondinelli to the Mechanochemistry discussions.
Okay, well, great. Thank you for that introduction. It's my pleasure to tell you about forces that shape chemistry. I'm going to describe how we're thinking computationally about chemical pathways to direct bond formation in solids. What I'm showing you here is a Northwestern University campus, and I'm sitting in my office in Cook Hall, which is just located right here. Unfortunately, it doesn't look like that today because it's mid-February, and the snow is, though, melting. So I'm James Rondinelli in the Department of Materials Science and Engineering. And if you're interested in learning more about the work that's going on in my research group, I encourage you to check out our website by scanning this QR code. In particular, today, I will tell you about mechanochemical efforts in the group. To give you an idea of some of the efforts happening in the group, I just want to show you the researchers who are actually performing the research in the group that I'll tell you about today. And the work in particular is supported by the National Science Foundation. I'll tell you more about how we got engaged in a part of this, the Chemical Center for Innovation that's supporting the mechanochemical research in just a moment. As an introduction, I am a computational materials scientist, and I lead the materials theory and design group. And we work in 3 different avenues. One is theory, integrated modeling, and simulation. So we're looking often at the electronic structure of materials, studying model Hamiltonians, understanding symmetry analysis, and trying to predict properties of materials. And that takes us to the second bucket of predictive science and design engineering. Along with that, because we're making predictions on materials, we often want to help accelerate their discovery in the laboratory. And so we're looking at infusing machine learning and AI methods to autonomize or accelerate the discovery platform. To give you some ideas of what we work on in the group before proceeding to the main topic of my presentation, I just want to give you some examples. So one area in which we're working is in what are called heteroanic materials, so materials that comprise more than one anion, and using that multi-anion chemistry to really direct electronic structure. We are also often quite interested in making properties of two different properties coexist in the same material. One example of that is a class of materials known as polar metals. And then we're very interested in functional materials. So another example is novel ferroelectrics, where we can design a material to have a spontaneous electric polarization or an electric dipole per unit cell, and that polarization can be switched with an electric field for low power ferroelectric memory devices. The other thing I wanted to mention before I continue with the technical part of the talk is that we're quite interested in this topic of what's called co-design. So thinking about the performance of a material in its end use in a device and how to design the structure and composition of that material from the beginning. Lately, we've been working on the design of novel conductors for interconnect applications in microelectronics to achieve scaling below 10 nanometers. Why this is relevant for this talk is that there's a key piece in co-design, which is manufacturing, or how you take the material and how you process it. And so this is in part how I became engaged in the CMCC, or the NSF Center for Mechanical Control of Chemistry, which aims to create new materials that cannot be realized by conventional methods. So if we're predicting materials in my group and conventional strategies to synthesize materials do not deliver them, we need new avenues to make them. And that's really what the CMCC is about. The CMCC is organized across two different thrusts. One is understanding mechanically driven organic reactions, that's thrust one, and thrust two, which is on oriented stress for solid state synthesis. These two thrusts are linked via an interdisciplinary toolset program which develops experimental and computational protocols to interrogate and develop mechanochemical processes. The work I'm going to tell you about today is supported by the CMCC under Thrust 2, and I just want to highlight what Thrust 2 is about. The goal of Thrust 2 is to understand and harness how patterns of forces drive mechanochemistry of chemical bonding, connectivity, and composition across material classes. The aim here is to understand a number of questions about how forces really drive the chemical reactions, among other questions. For the work I'm going to tell you about, chemical bonding, connectivity, and composition are quite important. And the way we think about it in solid state chemistry is that these are the three C's. These are the main building blocks of solid state inorganic materials. Chemical bonding, connectivity, and composition are built upon several aspects, which I'll try to explore in this talk. So one is just the choice of the atoms in your material. So you can tune the chemical bonding in the system by changing which atoms on the periodic table you have. Are they more electronegative or not, or more electropositive? Now, these anions will coordinate cations and lead to polyhedra of different sizes and shapes. And these can be connected in different ways, via corners or edges or faces. And then we can tile those connected polyhedral building blocks in various dimensions, and we can stack them in various ways. And these are the building blocks, again, of solid state chemistry, which often we can control by choosing chemistries correctly or cleverly on the periodic table. But now we want to be intentional about their assembly and how we direct them. And that's the idea with mechanochemistry. So what I want to tell you today then is how we think about advancing mechanochemistry in silico, meaning how we design and try to predict what the products might be of a mechanochemical reaction, a solid state mechanochemical reaction. This work, as I mentioned, has been supported by the CMCC and in fact was led by a very talented undergraduate student doing a research experience for undergraduates in the summer in my lab. And she was mentored, Faye was mentored by Jaewon Lee, a graduate student in my group. And the project has since been completed by Dawson Smith, another graduate student in my research group. So the three things I want to tell you about is how pressure can drive polymorphism in solid state materials. So this gives us the control over the three C's, and we obtain then different crystal structures. Briefly, how we model this type of mechanochemical phase stability. And then the heart of the presentation is really this mechanochemical transformation in salts comprising molecular anions. So I'm going to give you a very specific case. And if you don't want to listen to the remainder of the talk, I'm going to just give you the results. So you can tune out now if you like. The case study is on this mercury cyanamide compound, HgNCN. And what I'm going to show you is that we can drive a cyanamide to carbodiimide conversion of the molecular anion with pressure. So the approach here is that mechanochemistry enables us to achieve the same thing that we can do in aqueous solution by controlling pH. Pressure will mimic essentially a high pH, high basic condition, leading to an ionizing environment that allows us to control the isomeric form of the anion in this compound. Then I'll tell you briefly about the microscopic model that we built for the mechanochemical reaction. And here the summary is that pressure increases cation coordination, which leads to charge symmetrization across this complex ligand. And then I'll conclude by just telling you about future opportunities where I think combining experimental mechanochemistry methods with computation can allow us to predict new synthetic pathways beyond what's possible in solution chemistry. So let me jump in with just the introduction to the pressure effects. And what I want to describe is that pressure really has a handle and control over those 3 C's that I introduced for solid state chemistry: chemical bonding, connectivity, and composition. The effect is that we change these degrees of freedom, and then we can alter the electronic distribution in the solid, and this will allow us to tune physical properties. So I've given on this slide a number of examples. This is by no means comprehensive, but this is just some examples of work we've done or others that I find quite useful in the literature, where pressure can drive structural and electronic phase transitions. And this is very common in metal insulator transitions, either through chemical pressure or real physical pressure. In perovskite oxides, for example, you can drive a change in the electronic state, if it's an insulator or a metal, by changing the bandwidth of the compound using physical pressure or chemical pressure. You can also control magnetism and orbital physics, Jahn-Teller physics in these materials, and drive a change in the magnetic state, or even turn off magnetism. And here's an example of turning off magnetism in an iron compound, an iron mineral, jarosite, with high pressure going up to 50 gigapascals. Now, these types of examples occur, as I mentioned, often in oxides, and that's the community I'm coming from. And so I want to try to extend that to other complex materials in this talk. In addition, you can control linear and nonlinear optical responses. For example, the emission spectra or the color of materials with physical pressure. This is often done in perovskites, hybrid perovskites, to control their electronic structure. And then you can also derive what are known as reconstructive transitions, where you have a structural transition or a polymorphic transition, but you have to make and break chemical bonds in the process. One example of that is shown here in this carbodiimide compound, where shear stress is able to do something that you can't necessarily do without going to very high pressures in normal constraints. And this is happening in a class of materials known as supraceramics. And the idea here is you essentially have a salt where you combine a cation from the periodic table with a complex anion, and this is going to be a molecular anion. In all of these cases, pressure drives a change in the 3 C's. And so how do we model that effect of pressure on the chemical structure or the polymorphism? And the approach we're going to use for this talk, and the common one used in my research group, is to use electronic structure calculations based on density functional theory. And the way we do this is rather straightforward. We take a known material or a material which we understand at the macroscopic scale. We write its representation in an atomistic scale model. And then what we want to do is we would like to solve a Schrodinger equation that tells us how the electrons are distributed in that solid. The formalism to do that reliably and computationally efficiently is known as density functional theory, where we write the total energy of that system in terms of the electron density, and we minimize essentially the electron density. The workflow for these types of calculations is shown at the bottom of the slide, where again, we take the crystal composition, we have to specify the atomic structure and the geometry, we solve a Schrodinger equation, and then we can get out the electronic structure. In particular, for this talk, what we are interested in is in the stability of these materials and the distribution of electrons. So what does that look like then in our mechanochemical framework? So we take this workflow, and what we're going to then do is apply hydrostatic or anisotropic stress. These are the types of forces we would like to see applied in a mechanochemical reaction and understand how they affect the stability of the material, or if they can drive a chemical reaction. So we can then, in this process, compute free energies and formation energies of the solids and look to see how the potential energy landscape evolves as a function of stress. So you can, perhaps drive a chemical reaction and have to overcome this activation energy barrier to go from one phase to another phase. Mechanochemistry can catalyze that type of reaction and lower the barrier to get to that other phase. And that's what I'd like to explore. The system of interest, in fact, comprises this complex anion, this NCN2 minus anion, which is shown here on the right. So essentially, in its form, we have carbon bonded to two nitrogen atoms, and this molecular anion has a charge of 2 minus. So formally, it's isovalent to a sulfide ion and an oxide ion. And distinctly, unlike these two ions, it has this high aspect ratio, right? So it's this like linear dumbbell-shaped geometry. It also has strong covalent character and is intermediate in terms of its electronegativity, although it's a little bit closer to nitrogen than to oxygen. So it's some sort of pseudo-chalcogenide anion. And in this molecular anion, because of this double bond formation, we can in fact imagine that there's actually two types of isomers of the anion. We have the carbodiimide ion, which is shown here, where we have two double bonds and essentially the same carbon-nitrogen bond distances in the molecular anion. And then we have a cyanamide ion shown on the right, where we have one single bond, which is much longer than the triple bond with the other nitrogen, which is much shorter. So these two types of ions give us more degrees of freedom to access interesting solid-state structures. And in fact, when you go from sulfides or oxides to these molecular anions, we can change the crystal structure, say from that nickel arsenide type, which you might have for a chalcogenide binary compound, to something that looks more layered, simply because of the aspect ratio of this molecular anion. So the carbodiimide version of this binary compound will be layered compared to this more close-packed structure, as you see on the left, the nickel arsenide structure. Now, that gives rise to an interesting design space that as you tune the cations in this material, say if it's a ternary compound where you have two different cations, you can actually change the dimensionality. You can have 0-dimensional, 1-dimensional, and 3-dimensional structures. And interestingly, there's this band known as the Goldilocks zone in this family of carbodiimide compounds, where you can, in fact, really stabilize 2D structures. So understanding this stability and traversing it, not just with changes in chemistry, but mechanochemically, is something we'd like to explore. The family also supports a number of unique coordination environments. So to give you an example, lead carbodiimide, for example, supports a square planar 5-coordinate type configuration, and silver in this coordination in this compound adopts a tetrahedral 4-coordinate configuration. So these are not just structurally interesting materials, but there are many applications for them. For example, battery materials, in fact, supported by the fact that they can be layered. So this allows lithiation, for example, of the compounds. They've been explored for lighting applications. Substitution allows you to tune the luminescence of the materials. And then they've also been explored for photocatalytic applications. So you can effectively separate electron and volt pairs. I want to come back now to this isomerism possible in the complex anion. So you have either the carbodiimide anion or you have this cyanamide ion on the right. And the question we've been thinking about is, how do we convert between the two of them? And typically what is done experimentally is you have to change the solution chemistry to precipitate out that solid that you're interested in. And so you have to selectively choose the reagents as well as the cations and then the pH of the solution to convert between the two of them. What we did recently is we surveyed the available experimental literature on binary compounds hosting these anions, and we made this phase map I'm showing you on the left. So the vertical axis is the Shannon-Pruitt ionic radius, and then on the horizontal axis is the Pearson hardness, which is effectively a measure of the electronegativity, or more better described as how easy it is for the ions to release or give up their electrons. So what this phase map tells us is which cations, binary cations, want to adopt or have the cyanamide anion or the carbodiimide anion. And those are the blue circles. And then we have the red circles as the single and triple bonded anion. Now, what you can see is that softer cations, so lower Pearson hardness, will more strongly covalently bond to the anion, which will pull electron density off the anion and lead to this asymmetric configuration. So as you go into this red zone, you favor the cyanamide ion here on the right. Interestingly, there's some border that separates the carbodiimides that are all in blue and the cyanamide compounds, which are all in red. And one of them is mercury. And so this raised the question of, can we think about how to interconvert between them? So I want to focus on that mercury compound for just a moment. Now, looking at the experimental literature of how this compound is made, the carbodiimide compound can be made highly phase pure, and it's done in a pH of 14 solution. So what you do is you start essentially with mercury chloride solution, and what you do is have to deprotonate this complex. In that process, you'll pull off both hydrogen atoms, and with mercury in solution, it will then bind in this way. So we get ultimately a one-dimensional structure, which is shown here. It's orthorhombic. And this is the most stable form of the mercury carbodiimide compound. Again, achieved in a pH of 4. What you have essentially is almost linear coordination or linear carbodiimide anions. And then you have the mercury atoms in essentially one-dimensional chains over here. Now, there's another way to make this compound where you have the cyanamide anion. So again, a single and a triple bonded material. In this case, what you have to do experimentally is go to a more neutral pH, so make it slightly more acidic. And in this process, you only pull off one hydrogen, and that allows you to connect or link the nitrogen to the mercury atom. And the resulting structure is that now quite different. So you have essentially two-dimensional sheets of these mercury and carbodiimide anions or cyanamide ions, where you have one single bond and one triple bond. This is a monoclinic structure. So on the left, you have an orthorhombic structure. On the right, you have a monoclinic structure. Experimentally, you cannot convert this carbodiimide structure to the cyanamide structure. If you try to heat up the system to get to this metastable phase, essentially you just decompose the structure. It is possible to go backwards, but you have to essentially reflux the system. So you put it back in solution, in this very basic solution, and wait several hours at some finite temperature to get the reaction to reverse. So this takes us to the mechanochemistry aspect. And we wanted to address this question: can mechanochemistry help us to interconvert a cyanamide compound to a carbodiimide with pressure? So you want to go from this asymmetric environment to this symmetric environment. And the idea is we'll put that monoclinic phase, the mercury compound phase, under pressure to try to symmetrize the complex ligand. So what we will do is perform electronic structure calculations, as I described to you, where we can apply the physical pressure constraint. And what I'm showing you are the results of that simulation for the cyanamide phase that was on the right as a function of pressure. So upon increasing pressure, we see that the volume dramatically decreases. So that's not surprising. It's a two-dimensional compound. We start to apply pressure, the volume starts to shrink. And that monoclinic structure has a beta angle. So the lattice or the unit cell does not have orthogonal interaxial angles. And it slowly decreases, and then it jumps up and then starts to decrease smoothly again with increasing pressure. What we can do is look at the changes in the electronic structure and the unit cell as this is happening. So at 0 gigapascals, the ambient pressure case, this is what that structure looks like. I'm taking a slice through the structure, and you see charge density contours projected onto it. So on the left, at the 0 gigapascal structure, you see the cyanamide anion, and this electron density is asymmetric along the anion. So this reflects the single and triple bond character that we have in the ambient pressure case for the mercury compound. Now, upon increasing pressure, we see the volume will start to decrease and the beta angle will start to decrease, which is defined here on the lower right. And then we have this abrupt change. And what happens, you can see, is that the anion rotates in the unit cell. So instead of pointing from the upper left to the bottom right, it points from the lower left to the upper right. And then with increasing pressure, the beta angle starts to decrease again. And if we look closely, the charge density starts to symmetrize. So that we qualitatively see that these contours look effectively the same at high pressure, 660 gigapascals, and they reflect something like an avocado shape. They're symmetric about the center of that carbon atom. Now we can interrogate that in more detail, and what we can do is compute the bond lengths. So in the cyanamide phase, or with the cyanamide anion, we should have two distinct bond lengths. This is corresponding to the single bond and that triple bond. So as a function of pressure, we're plotting the computed bond lengths and the computed Bader charges, which reflect essentially the amount of electron density on the two different ions. As you can see, with increasing pressure, we go from two distinct nitrogen atoms to essentially identical nitrogen atoms, which have the same bond lengths. And that charge localized on the on the two nitrogens is effectively the same when the bond length symmetrization also happens. So what we find is this conversion of the cyanamide anion to the carbodiimide anion above 50 gigapascals in this binary mercury salt. Again, there's no change in composition. We are just reorganizing the electron density along that anion. Okay, so that's cool. Does it really matter? So that's an interesting question. So we can also compute the electronic structure, as I said, using density functional theory. This is something we more or less get for free when we perform these simulations. And what I'm showing you is the electronic density of states for the compound as a function of pressure. Each panel corresponds to a different applied pressure. It's insulating at ambient conditions, as is expected. These materials, once synthesized, are these white powders, essentially. And as you apply pressure, what we see is that the band gap, the energy gap that separates the filled valence band states from the empty conduction band states, which you can't see at the ambient pressure case, start to come down in energy. So these states shown here move closer to the zero, and across the phase transition into the carbodiimide phase, you see that the band gap effectively closes. In fact, there's a small density of states, so a small concentration of electrons, which means that the material transforms from an insulator to a metal. One of those types of transitions I mentioned are known to be possible with pressure and often explored in complex correlated oxides. Here we see that also happens in the system, in this mercury compound, although I should note that this compound is not likely to be a good metal just because the number of states available is very low. So this is rather reflective of the fact that it's probably a bad metal or a poor conductor or not conducting at all. So to see this charge density changes that happen, or this collapse of the band gap, we expect the electron density to start to be delocalized. So a metallic state would be described by delocalized electrons or itinerant electrons. And on the right, I'm showing you the electron localization function computed by density functional theory. And this is really just a measure of how localized or delocalized the electrons are in the system along the anion chains. So at the 60 GPa case, once we've formed the carbodiimide phase, you can see that we have continuous charge density. And in fact, our color map corresponds to a green, which has a value of a 1/2. And this is the value we would attribute to something known as the homogeneous electron gas. And this is where we expect that metallic state to appear. And it's consistent with our description of the electronic structure. So let me now describe how we make this connection between the mechanochemical effect, so the pressure effect, and what is happening in solution when you precipitate one or either the first phase with the cyanamide compound or the second phase with the carbodiimide compound. So what we find is that high pH, again, experimentally, stabilizes the carbodiimine phase. It's strongly alkaline, and it deprotonates that entire NCN unit. It pulls off both hydrogen atoms. Then the mercury goes on, and then it leads to this symmetric bond environment. Now, in the lower pH, the more neutral case, this happens in a sequential way. So what pressure is doing is essentially creating an analogous ionizing environment for the NCN ligand. And in the process, it also increases the cation coordination. It's making the system denser and leading to higher coordination. This higher coordination requires that there's charge equilibrated across the anion because it sees more atoms around it. So that charge distribution has to be more symmetric. And that's what I show on the next slide. that high pressure will favor this more densely packed symmetrical structure. And we see a coordination change in the mercury atom. So it's in the carbodiimide phase, what we have then is the anion seeing more mercury atoms around it. And it goes from a linear coordination to effectively a square planar four-coordinate geometry. And so what happens is the anion can see more mercury atoms, and this leads to not only a symmetrization of the electron density across the ligand, but the cation, the mercury cation, effectively has some orbital rehybridization between the s and p states. And that we can calculate directly using our electronic structure calculations using what's called this orbital population analysis. So what we're doing is essentially projecting or counting the electrons localized on different orbitals in our density functional theory calculations. And you can see that these start to evolve and equilibrate with increasing pressure. So let me come back. This is the last topic I want to mention is if we go back to our phase map of ionic radius and Pearson hardness for the different anions, we see this phase or this effective phase boundary between the cyamides in red and the carbodiimides in blue. And we explored this transition mechanochemically with mercury. The question is, for other compounds near this boundary, do they also exhibit a similar transition? And so we've started in the group to look at these transitions as well. One example I'll just provide for you is in hafnium. So in the hafnium compound, we also find that we can drive this transition between the cyanamide phase at low pressure to the carbodiimide containing anion phase at high pressure, and it occurs at a much lower pressure, which is nice. So we're starting to look at the role of this cation, the cation size, the A site cation, in controlling the critical pressure for the phase transition here. The next question we would like to answer is how can we achieve essentially the opposite conversion? So we've been going from the left to the right, the cyanamide to the carbodiimide phase. And what we'd like to know is, can we go from the carbodiimide phase to the cyanamide containing phase? Now, this probably will require a change in the type of stress or using oriented stress, as we mentioned, is one of the tools that we're pursuing in Research Thrust 2 of the CMCC. So we're looking to do that in the future. So with that, I just want to summarize and try to describe what I've tried to tell you about in the presentation. Mainly, we've been thinking about how we link stress or mechanical force to chemical bonding, connectivity, and composition outcomes. So what is the product and how can we reverse them? Again, these are the 3 C's of solid-state chemistry that we want to have force control over. And then I gave you a use case for this mercury carbodiimide compound where we can mechanically control the state of the mesomeric forms of this complex or molecular anion and binary salts. The short of it is that there is a mechanochemical analog to pH, solution pH, that allows us to control which polymorph forms. Again, low pressure is similar to low pH. High pressure is similar to high pH. And you can then use mechanochemistry to control this conversion. And then the last thing that I want to highlight is what the important role of computational materials models are in understanding mechanochemistry. When these reactions happen experimentally, you get the results. There are in situ means to examine these types of reactions, but really understanding what the driving forces for what leads to a mechanochemical reaction and how it connects to a solution-based chemical reaction requires some sort of model. And in this way, in this regard, it's essential to complement experimental investigations with computational material science approaches or computational chemistry approaches to begin to build out the chemical intuition that will allow us to directly understand how does force govern mechanochemical reactivity. So with that, I just want to conclude and thank you for your attention. If you're interested in these topics or any of the other type of research happening in my group, feel free to reach out to us. So with that, thank you.
Thank you for your presentation. So we have a few questions. First one, can you please clarify the direction in which the pressure is applied? Is it only along the C-axis?
Yeah, great. That's a great question. And I apologize for not being as explicit. So in this study, what we're doing is applying hydrostatic pressure. So it's uniform stress along all directions of the crystal. So we're not applying uniaxial stress, but it's a hydrostatic pressure that's being applied.
A related question, could the pressure be applied asymmetrically?
Yes, this is a very good suggestion, and it connects kind of to somewhat to the question I pose at the end, is that you can apply asymmetric pressures, and this is typically a form of a shear stress. So you would think about applying a pressure on just two different surfaces, and that should, in principle, allow you to access a different state of the anion. And this is something we're looking to in this project, as well as throughout in several material classes.
Thank you. Can you comment on the accuracy of the functional in predicting the high pressures?
Yeah, this is a good question as well, mainly maybe for the experts doing these types of electronic structure calculations. For phase stability in this system and in many systems, we often do analysis of the dependencies of the prediction with respect to this functional. So this pertains to an approximation in the density functional theory framework about how we treat the exchange and correlation energies. So for the study that was done here, our results are based on generalized gradient approximation methods, basically what's known as a PBE functional. We've also repeated this set of calculations using what's known as a meta-GGA, which includes a more accurate description of the kinetic energy of the electrons. And there we see the same results. And in fact, these meta-GGAs get a better bonding description of the short and long bonds you have in the cyanamide anion. And so this is quite important in describing with higher fidelity the molecular anion. In terms of accuracy, the results here we trust with to the order of several millielectron volts per atom.
All right, maybe related to the high pressure. How does the predicted transition pressure compare to experimental values?
So the predicted transition for the mercury compound is of the order of 50 gigapascals. Now this prediction it remains a prediction, so it hasn't been experimentally tested yet. So that's something we're interested in. 50 gigapascals is by no means an easy experiment, but it's not the most difficult pressure experiment. What we're looking for is trying to bring down that critical pressure, which is motivating, as I mentioned at the end, our search with other binary cyanamide compounds where we change the cation to reduce the critical pressure. So that's one avenue we're using to reduce the critical pressure. For high pressure solid state transitions that are often explored in the literature, the other thing that we need to be mindful of is that you can transform the material into an amorphous phase. And that's something we haven't yet explored to see the phase stability between the crystalline compounds we're looking at and whether or not the amorphous analogs might result. Yeah.
All right, let's wrap up with just one more.
Okay.
Are there many other chemical species that could be manipulated using this approach?
Yes, that's a good question. So the mechanochemical effect here is really this deprotonization of the molecular anion. And so if you're building up a hybrid solid state materials, either comprising molecular cations or molecular anions, you can make this connection between what the pH of the solution is and the mechanical force. So we believe this is going to be a general approach. And in the future, we're going to look at a range of compounds that comprise molecular anions.
Great. Thank you very much. Thank you again, Professor Rondinelli, for that outstanding presentation. And thank you so much for joining us. Just a reminder that all of our previous seminars over the past few years are available to watch anytime on the YouTube channel. We also would like to hear your feedback on the seminar series for ways to improve, so please feel free to use the QR code here or available on YouTube to let us know how we can improve the program. Lastly, we have a great group of speakers planned for the upcoming months, and we hope that you will join us for all of them. Thank you again.